Hello everyone, my name is Bùi Tiến Cường from PIDEO Lab. Today I am going to present a paper named Path Integral Guided Policy Search. My presentation will follow the flow of the paper as you can see here. First, let me introduce the problem addressed in this paper. As you know, reinforcement learning and policy search methods have shown considerable promise for enabling robots to automatically learn a wide range of complex skills. Recent results suggested that these methods can be extended to learn nonlinear policies that integrate complex sensory information and dynamically choose diverse and sophisticated control strategies. However, real-world robotic tasks are challenging, and it's not straightforward to apply deep reinforcement learning directly due to high sample complexity of these methods. Using a set of local policies optimized on specific instances to train a global policy can be an alternative solution like guided policy search methods. However, prior implementation failed to optimize policy on tasks involving complex contact with switching discontinuities such as door opening or pick-and-place objects. In the paper, the author proposed a novel method for local policy optimization using policy improvement with path integral, or P-squared. I denote local policy as LP for brevity. This method enables GPS to train on new task instances in every iteration by extending the on-policy sampling approach proposed in recent paper named MDGPS. It increases the diversity of experience to improve generalization. Once the robot experiences the world, it can continually learn new task instances. Policy search methods have been used in robotics for a variety of tasks. However, the high sample complexity problem causes it to be hard. Guided policy search decomposes the policy search procedures into trajectory optimization and supervised learning of general high-dimensional policy. Path integrals have been successfully used to learn parameters of trajectory-centric policies, and it does not compute a gradient. Stochastic policy search methods limit information loss between updates using KL divergent constraints. Let me provide some background concepts of the paper. First, the guided policy search is to solve the poor local optimal problem of policy gradient methods. A sequence of actions and states can be represented as a trajectory. A trajectory-centric algorithm learns simple controllers for trajectories. Path integrals is a model-free reinforcement learning algorithm based on stochastic optimal control and statistical estimation theory. The time-varying linear Gaussian controllers representing the local policy are given by P. Then we compute cost to go S at the summation of trajectory. Then we compute the cost to go S at the summation of trajectory from the time step T. Probability P for each sample I and each time step T using softmax distribution over this formulation of S with a temperature term eta. After computing the new probability P, the policy is updated according to a weighted maximum likelihood estimate of policy parameters, which are the means and covariances of sample P forward control K bar of sample I at time step T as follows. Question 1. What are the roles of path integral for this method? The role of path integral for this method is to improve the local policy by transforming the stochastic optimal control problem into the approximation problem of path integral. Let's move on to the essential part of the paper. First, let's talk about path integrals for guided policy search. We aim at limiting the change of policy to avoid sampling too far from unexplored policy regions, thus letting the model gradually converge towards the optimal policy. The policy update step can be controlled by varying the temperature eta of the softmax probability P. We employ an approach similar to relative entropy policy search to determine eta. Next, the local policy P is augmented with a KL divergent constraint against the old policy P bar as shown here. The Lagrangian of this problem depends on eta. We compute the temperature eta at each time step separately by optimizing the dual functions with respect to cost to go of the policy samples. We'll discuss the global policy sampling and initializing procedure. The standard GPS framework has the limitation of being constrained to a fixed set of task instances and initial condition for the entire learning process. If we use pi squared with the constraints against the previous global policy, we do not require previous local policy for the same instance and can sample new instances at each iteration. The optimization is now constrained against the KL diversion to the old global policy and can be solved through optimization of temperature eta. The right-hand figure demonstrates the algorithm of p-squared with global policy sampling. After performing one-step local policy optimization with p-squared, the update controls are fed back to the global policy with supervised learning. The covariance of global policy noise is updated by averaging the covariance of the local policy at each iteration. The optimization is performed in the local lower dimensional action space with a trajectory-centric algorithm. Global policy is initialized by some GPS iteration with pGPS. We also initialize the local policy with kinesthetic stitching to provide the algorithm with overall structure of the task at the start of the training. After initialization, the global policy can already occasionally perform the task, but it often overfitted to the initial task instances. By training further with global policy sampling on random task instances, we can greatly increase the generalization capability of the policy. The model goals are to solve complex object manipulation skills such as door opening or pick and place object. Therefore, the policies interpret visual input to localize the object of interest using convolutional networks. The training procedure includes two steps: pre-train the CNNs and train the feedforward layer with pGPS. CNNs incorporate information at different scales via pooling and skip connection to limit the computational overhead. The CNN model is first pre-trained with two sets of image, objective objects, and the convolutional networks are first pre-trained with two sets of images. Then, the model weights are updated using SGD with momentum and standard Euclidean loss. The fully connected layers of the network are trained using path integral policy search to produce the joint talks, while the weights in the convolutional layers are frozen. Note that we add to a model a set of images collected from first camera image feature point to allow the policy to remember the location of object in case of occlusion by the M. Now, let me quickly show the performance of the proposed method. Before moving on to the experimental results, let's take a look at the experiment setting here. The paper shows the performance on the door opening task. After recording the door opening motion from the demonstration, the door is displayed by 5 cm away from the robot. The path integral version of GPS outperforms the standard LQR version. Question 2. Why is the success rate of baseline model in the figure 4 too low compared to these methods? LQR could not handle the nonlinearity of dynamics due to the contact with the door and discontinuity in the cost function between moving and not moving the door. The paper shows the performance on harder tasks pick and place. In this task, the goal is to adapt the demonstrated trajectory to displayed and rotated objects. Again, the PGPS methods show the best performance, while LQR cannot perform on this task since the cost function could not be modeled with a linear correlative approximation. The training is longer than the door opening task due to the hardness of this task. The goal of this experiment is to compare with P-squared GPS and global policy sampling. The green one is the hybrid algorithm that uses P-squared to optimize a local policy, but we use the per sample probability P as weight for global sampling training. PGPS achieves the lower cost at conversion and fewer samples. The author observes that the others have a tendency to go unstable without achieving conversion when training complex neural network policies. Finally, the paper shows the evaluation of the generalization performance of guided policy search with pi-squared on randomized instances. So, as to determine the degree to which global policy sampling improves generalization, when applying global policy sampling in the door task, the model aims to teach the robot to open the door placed at any post inside the training area. The final policy is able to open the door in 93.3% of the test instances. In the pick-and-place global sampling experiments, the model teaches the robot to pick up a bottle placed at any position inside the predefined rectangular training area of table and place it vertically at the goal position. After finishing the training with global policy sampling, robots succeed 86.7% of the time. Again, the performance is a little lower than door opening task due to the task complexity. Question 3. Can you comment on the generalization of this method to other complex robotic tasks, such as fitting two objects, like bottle and its top, I guess its lid? This method can be applied to other tasks with two steps: learning local policy to let the robot experience the world, and then generalize to global policy to find optimal policy and handle various situations. In conclusion, the paper presents the path integral guided policy search algorithm evaluated on the door and pick and place. Thank you for listening.